Now let's say that we have to verify this design. This is a very basic design which has a certain set of inputs and a certain set of outputs. How do we verify this design? The very basic thing that we can do is provide all possible value to the inputs and verify that the outputs are correct. And then if we want to verify it in more corner cases, we might want to exercise those cases and make sure that the outputs are correct in those cases as well. Now let's assume that this is an ALU design which performs a certain set of operations like subtraction, addition, multiplication and division. How do we ensure in that case that this design works correctly, given that it has two set of 8-bit inputs and a 16-bit output? So the first thing that comes to mind is that I'll provide all possible values to the inputs and check whether the outputs are correct, and then check different corner cases based on the specifications of the ALU design to make sure that the outputs are as per required. What is a test bench? Test bench is actually the code which is used to create a predetermined input sequence, which is called a test case, which is fed to the design and the response is observed. So all these operations are performed by the test bench. In verification, the test bench provides the inputs and monitors the outputs. The challenge in creating a test bench is that we have to be sure of the test cases that we want to provide to the design. That is the stimulus that we want to provide to the design. So we have to know what all test cases to write and what should be the checking mechanism. So this is a typical test bench in which there are a certain set of test cases written which are fed to the design one by one, and on the other side of the design the observer part is there, which could be a data checker or the result checker and coverage collector. Now this is how a particular test case works. It is fed to the design and it goes through to the checker, the coverage collector, and same thing applies with all the test cases. So that means when we provide a set of inputs to the design works on that, provides the output. That output is monitored by the checker to make sure that the output is correct, and the same output is also checked by the coverage collector to make sure of all the stimulus that has been covered till now. So in this way multiple test cases are written, they are fed to the design and they are observed by the checker and the coverage collector. There are different types of functional verification. Simulation based verification, which can be directed verification or random verification. So the difference between directed and random verification is that in directed verification we know what are the inputs that we are going to feed to the design, but in random verification we are not sure about the inputs that are going to be fed to the design. The input, the stimulus is random. Then there is formal verification, assertion based verification and coverage driven verification. In assertion based verification we have a set of assertions which are written to check the negative scenarios of the design. How does the design behave when a wrong scenario is fed to the design? Is the design able to complain about it? Then the coverage driven verification. In coverage driven verification we figure out the different points that we want to verify using the design and provide stimulus, and finally check if all those points, which are called cover points, crosses, are getting covered or not. So when we are able to achieve the 100% of coverage, we can say that we have completed the verification, and that verification is called coverage driven verification. Similarly, when we are able to achieve all the assertion firings, that is called assertion based verification. This is the flow of a typical simulation based verification. Once the design is ready, the first thing that we do is to create a test plan. That is, we write out all the test cases that we want to feed to the design. We create the stimulus using those test plan, and in parallel we also create a coverage matrix. Now what is a coverage matrix? Coverage matrix, as we discussed, is the set of points that we want to verify. Let's say in an ALU, what could be the coverage matrix? we would like to cover whether all possible inputs have been fed to the design. That could be one possible way. The other matrix could be that in a division case, let's say in a division case, did it ever happen that the second operand was 0? Because division by 0 is not allowed, so we have to make sure that that is never fed to the design, and if it is ever fed to the design could recover from that correctly. There could be more coverage matrix as well. So once the test plan and coverage matrix are ready, the test plan is actually used to create the test cases and it is fed to the design. And in case of anything wrong happening in the simulation, we debug that using simulators like Questa simulator, VCS simulator and NCSIM simulator. There is another thing in the simulation, the flow of simulation based verification, which is called regression. Now, as we discussed, using the test plan, we create a number of test cases. We debug each test case independently as well, and we run all of them together. In regression, we run all the test cases together and observe the response when all of them are run. And in case of a failure of any of the test cases, we go back to the previous step and debug the test case in particular. So in this way, we make sure that all the different corner cases are verified and the design works in all of the cases. So the traditional approach of verification was directed verification. In that, we used to manually create the test cases based on the features to be tested. That is the test plan that we have created. We create manual test cases for all of them. It actually takes less time to start writing test cases. That is, from day one itself, I can start writing test cases, but it takes more time for completion. It also works well for smaller designs, because for smaller designs, we might be able to think of all the possible scenarios that we want to check the design in. But for growing size of the designs, this approach encounters many missed functionality issues, because we might not be able to think of all the scenarios. And also, even if we are able to think of all the scenarios, it will be time consuming task. And the worst of all, this test bench is not reusable. We will not be able to reuse the same test bench in another verification. So these are the drawbacks of traditional approach. And the modern approach is called constraint random approach. To overcome the limitations of traditional verification and improve verification productivity, the only way is to reduce the time that it takes to create the test cases. Using this approach, which is called the constraint random stimulus generation, the different scenarios, that is test cases, can be generated in an automated fashion under the control of a set of rules which are called constraints, and those constraints are specified by user, which in turn is specified by the specification. Different programming languages like System Verilog, they provide capabilities to create these complex verification environments called the constraint random stimulus generation and functional coverage. These features allow the users to develop test benches that automate the generation of various scenarios for verification. Now let's say there are multiple complex scenarios which the user want to verify. So one way of that is that the user creates those test cases manually, or the other case is that he creates a random generated stimulus and runs multiple test cases in which different scenarios will be created by the stimulus generator itself and observe the response. So the second approach in this case, which is called the constraint random approach, it will take less time for him to create the test cases and he can focus more on the debugging part. He will be able to achieve more scenarios in lesser time. This is a flowchart of a typical graph which shows the time consumed in a directed versus constraint random approach. So as we discussed,